and let me share. I guess it's easier to use the tab to write. So let me move away some of the stuffs here. So I guess let me start with like some review again of like what we had so far. Um, hmm, okay, seems like wait a sec. Okay, it should be working now. So let's see. Let me erase this. So I guess I want to emphasize one thing again. Like be careful. Like in statistics, kind of like stochastic cell processing, probabilities, and so on, and information theory. Whenever we talk about random variables, there's a difference of like uppercase and lowercase. I try to be careful, but sometimes I have to confess that like I sometimes I kind of was not careful enough when for my handwriting. Um, so when you are looking at uppercase, it's always like it's a random variable. So in the sense like you think of this as a random variable. So like each time you look at this, like it should be different things each time. And when you talk about small x, it's a particular realization of that random variable. So therefore, like I would say that most of the time, for example, when you write probability, it makes sense to write px, but it's not does not make too much sense to write like p capital X, because like when you write like this is actually a random variable because x is a random variable, p is really a function, like px is a random variable itself. So unless you know what you're doing, like most of the time you should write like this. But on the other hand, you know the entropy, like hx, we write as like expectation minus log p, and know that this is like capital X here. So because like you're doing expectation of a random variables, right? So if this is not random, if this is something deterministic, this is just a constant, then taking an expectation of a constant, that's fine, but it just give you a constant. So therefore be very careful with the notation. For example, like when you have hx given y, okay, let me maybe like I give you a quick question here. So a and b here. So what it should be like expectation minus log px given y, or expectation minus log px given small y. So which one should be correct? So anyone else? Yes, be very careful. Okay, here like they mean different things. Like when you write like this, it means different things. This one will be more or less means that like x given y equal to some small y. So know that like hx given y here is actually the weighted sum of this p y here, sum of a y here, hx given y equal to y here. So so therefore you see like this notation is pretty subtle. So when you say expectation of this one, um, by convention, you see this is a random variable, right? So you know this expectation is like expected over x and y here. But on this one, it's only expected over x. So therefore, if write this one, like the first one explicitly, the first one should be equal to summation. I'm just assuming all discrete random variable here. So it's a summation pxy, right? And log p x given y here. And on the other hand, the other one is actually, because I now you look at y is deterministic, right? This is actually, when I write like this, is really a expectation only over x. So it will be something like p y, sorry, px px given. Actually, this have a little bit I should say, like notation here has a little bit ambiguity as well. Like probably like it's better to write like this, like expected over like x given y, something like that. So but this one, if you know the um if you omit that, like even you omit that, because people know understand this conditional entropy and so on, like they realize that you are actually meaning this. Yeah. But um but you see, like this one is exactly this notation is h is given y equal to small y here. And when I, for example, if I put this like into here, then I have like y p y sum over x here, p x given y minus sign here, log p x given y here. So then this together will be like pxy, right? Pxy, so I have like sum over xy minus p xy log p x given y. So this is exactly like hx given y here. Yeah, in this form here. Yeah, here. Um. So yeah, that's one thing I find that like maybe several of you are um uh, may not aware of that, and maybe I didn't emphasize enough for that. So therefore, like this cap and like capital and like upper and lower case is important, like, whether you are writing upper and lower case. And now let me, okay, um maybe I just start a new page. Okay, today what I want to start first is just a again similar to some kind of review, because I think I mentioned that before, is a doing some kind of chain rule on the information measure, like for example entropy, mutual information, and so on. Maybe we'll focus on entropy first. So for example, like if, when we have like earlier hxy, let's say hxy, and know that like this will be like expected minus log pxy here, and I can write it as a expected minus log p xp y given x, right? So then I expected minus log px and plus expected minus log py given x. So therefore, like this one give like hy given x here, this one give hx here. So as we mentioned earlier, this is really very reasonable, right? Very intuitive. So you look at like the total amount of information like for x and y, it will be like the amount of information for x, and then I add it with the amount of information of y, given that we already know x. So we can have like, generally speaking, we have a chain rule. So now it's good for me to introduce notation like this, like x1, x2, up to xn. That's a very convenient shorthand notation that I guess I roughly mentioned that, but didn't emphasize that enough. So I can write like this, say for example, xy to the power n. Note that this is not a power or something. It's just accounting, like for example, like from x1 up to xn. Hy, yes, it's symmetric. So therefore, like you have um, it's hy plus hy hx given y as well. Yes. Um, and uh, and so this one I can also write like another notation. This is just a definition of notation. So if you just write like hx to the power n, um, in this context, at least like in information theory, often this is not a power of this random variable, but instead it's like um, would be like meaning x1 up to xn. Yeah. So this way kind of like very important. Like after like sometimes it may have ambiguity. Like maybe like the author really means the amount of information of the. But usually this for example, at least for discrete random variable, you will never do that because like okay, what's h x square? This can be a tricky question, but like if x, let's say x is like mm, honestly, it's probably an interesting exercise. Like, let's see. In general, like if I have hx and hx square, uh, what should I have? Like I should have like this or like this. Let's say this is A or B. Uh, X is discrete. Let's say this is discrete. X is a discrete random variable. For continuous, I think yeah, it's hard to say. Like continuous probably is hard to say. Say if X is discrete, like oh okay. Yeah. I'm sorry. Wait a second. Um Okay, I immediately say this, and I say this like this is bad. Like, okay, what I mean here is like, sorry, like this is like the usual notation here. Here, I'm really meaning that like this is x is a random variable, and then I take the square of that x. Now I'm asking like, is hx should be bigger or hx square should be bigger? So I'm not referring to the usual convention in information theory. The usual convention here will be meaning hx1. I mean, this one will mean hx1, x2, right? So yeah, I don't mean that actually. So, but there's some B, some A, and actually you can do some example yourself. For example, you think of um uh it depends on the domain here, but in yeah, actually the question is has no ambiguity. You should always be like a here is more reasonable. Um, just because this x squared is uh it's a function basically. Square is a function, so given x, x square is given, right? So in the sense that if you have hx squared plus x should be equal to 0, right? But on the other hand, you shouldn't have hx given x squared is equal to 0. So it may or may not happen. For example, like it depends on, in this case, it depends on the domain. For example, if you can x is can be -1, let's say, right? Or you take the square root of something, like for example, given x squared is equal to 1, then you say like I'm considering like all natural number or like all integers, then my x can be 1 or -1, right? So therefore, like given x squared, like this doesn't need to be like equal to 0. So Then what we have is a, let's see, since I have this one, I have a hx square. Uh, let's see, how do I show that? Yeah, let's see. Hx plus hx given, sorry, yeah, hx plus hx square given x, that will be hx mx square, right? And but this will be bigger than, always bigger than hx square, right? So just because you have two random variables here, um, oh, here, like that's no law, the interpretation here will be just taking a square of that random variable. So uh, literally, like if I have something discrete, let's say I have integer like 0, 1, it can be all integers, or like okay, let's just assume the domain is like all integers here. Then literally you have a random variable that x can be any of these integer. It can have some distribution, right? I can have a PMF, maybe like my x. Let's say I define precisely the PMF as a px that is can be equal to maybe 0.5, or let me just just plot it out. Let's say I can have something like that. This is 0, maybe like -1, 1, -2, 2. And maybe I just have all these values to be have equally likely. Let's say this can be my probability of x, the PMF for my x. Then my PMF for my x square, let's call it like y, something like that. Then it will look like something like that way, I guess. It will look like 0, um, can be 1, uh, 1 and 4 way basically, right? Square here can be 0, 1, 2, 3, 4. Let's see. I guess like 1 and 2 are more like, let's say 1 and 2 would be more likely, right? We'll have like double the probability here than 0, right? Because here like 0, I can only have 1/5 of the probability to be 0, but I have like 2/5 of the probability to get one way for y, for x squared equal to 1, because I can have x either equal to 1 or -1, right? And when x is equal to 2 or -2, I will have like x squared equal to 4, right? Something like that. So I will have a distribution of x squared will be like this. Yeah, then you look at that, the function here, like uh, given x squared is known, right? So therefore this is actually equal to 0. So then I will have hx is bigger than hx squared, as you can see here, because this is equal to this guy. And then this one, why this one is bigger than this one? This one is equal to x squared plus x squared given x, right? And all this entropy has to be bigger than equal to 0. So therefore, like, this will be bigger than equal to hx squared. So is that clear? So sorry, like it's a digression. So it's a digression here. But in general, you can see that like in general, you can see that I guess I should just hand up this one. I don't know what. Yeah, this is 405, but yeah, I guess probably like it's okay. So um in yeah, you can see that in general, like as long as you have a function like let's say hx, and you have a function hfx here, you always have something like that, right? F is a function because given x, fx is given, right? So by the same argument there, by the same argument here, I will have essentially the same thing here. h x plus h f x given x. So this one is equal to 0. So therefore, this is equal to hx, and this is equal to h f x and x, and that is equal to h f x here plus hx given fx, right? So therefore, it's like bigger than equal to hfx. So, and if this f function is a one-to-one, then you will have x is equal to x squared. So for example, like if you have, let's see, what function it will be one-to-one. For example, if I have like, instead of x squared, I have x plus some constant here, it's just a shift, then that would be just equal, right? That two entropy should be just equal. So, okay, sorry, like all this is a digression, but I'm just saying that this is a, just, so, but you see why, therefore, like, most of the time people will not ask question like, what's the entropy of like x to the power n, because like, it's, if you assume that, for example, consider x is all positive number, something like that, then that to the power n is actually a one-to-one, it's a one-one mapping, because if we only restrict to the positive domain, the real to a positive number, then you can basically, the inverse is also exists, right? So you need inverse exists. So therefore hx will be just equal to xn hxn. So that won't be a very interesting question to ask. So therefore, when you see notation like that, often it's just meaning that it's a asking like the entropy of like a sequence at x1 up to xn. Now this one here, now I can expand that, but let me just forget. I mean, just skip those steps there. So I can write immediately as hx1. So you can easily just expand that. You will just get this, but I'm basically skip that here. X2 given x1 and x3 given x2, x1, and so on. And maybe I write one more term, but hx4 given, I can write this shorthand notation now, given x3 here, and so on and so forth. Plus hx and given xn minus 1. So this is a train rule for that. And I can also have train rule for just like x and given y, let's say. And maybe I do one of these, like x1, x2 given y, x1, x2 given y. So we do this again, expectation minus log p x1, x2 given y. Then again, we can expand that, expectation minus log p x1 given y minus log p x2 given y x1. So then this gives me like hx1 given y, maybe I plus expectation minus. So this give me plus hx2 given y x1. Yeah. And so in general, I will have like hxn given y is equal to hx1 given y plus hx2 given x1 y, and so on and so forth. Like just as you expected, I would say, and minus m y. Now, remember that we have the difference of the entropy and the conditional entropy. So remember that like something like if I have like x and y, hx and hx given y, I have this one, hx is always bigger than equal to hx given y. This is like we I don't know any of you remember the, yeah, I think probably you don't, like it's like conditioning, they call it condition reduces entropy. So it's whenever like this is a very reasonable way. If the way you look at that is like, okay, if I know something already, then the remaining information will be less, right? And do you remember like what's hx minus hx given y? So maybe a question here. So we mentioned that like I think like before the homework, like just before the homework, uh, probably 2 classes ago. Yes, that's the mutual information. Oh yeah, just a slight thing that want to emphasize. You want to, for the mutual information, um, the kind of like punctuation in the middle, you want to use the semicolon instead of a comma, um, because you can have like more than 2 variables. For example, if you have like x, y, and z, then you need to know like what you're talking about, whether you are talking about the mutual information between x, y, and z, or like between uh, x and y, z, something like that. So even though if only 2 variables, it's kind of like it's understood that like, yeah, but still like it's actually a typo, considered as typo. Even though like, I see this typo like in papers as well, in even like accepted papers. Um, so this is like ixy, and let's look at ixy again. Ixy, this one. So this one is ixy, right? So this one is ixy. If I use the expectation notation here again, I expand using expectation, I have minus log px, then plus expectation minus log px given y here. So again, be very careful with this like uppercase, lowercase thing. Like here, it's just expectation over x and y. Here is expectation only over x. Um, but it's okay. Like we mix them together because the beauty here is if I just put them together, expectation minus log p, or like maybe I use like px uh, given y minus log px. Let's say now if I do that, now the whole thing should be expected like over both x and y, right? But here, like if I do expectation here on y, because it's this thing does not depend on y, then doing an expectation on y, it will just become itself basically. Uh, I mean, like if I do this expectation of both x and y, I have like um, supposedly I have like sum over x and y, or like some, let me split that, sum over x and then sum over y minus log px, right? Not small px here. Uh, yes, the can, or yes. Let's see, wait a sec. There's a minus sign here. I'm sorry about that. Yeah, there should be a minus sign. So therefore the minus sign got cancelled. Um, so and yeah, for this one here, back to this one here. If I sum over y, uh, okay, sorry, sum over y, I need to have like pxy as well. Like yeah, this is expectation, right? This multiplied by pxy here. So this one does not depend on y. So I will essentially just say sum over y for pxy, right? So this will just marginalize this thing to like this whole thing together. It will just become px, right? So then will be just as before, like just as equal to this original one. This one should be sum over x px minus log px. So therefore, like I was not cheating like when I absorb this thing, even though like these two expectation is like expecting on different things. Like again, like this one is expecting over both x and y, this one is expecting over x. Now when I absorbing that, like actually I jump some step when I do that. Like this should be very careful. Like even though like this is not a mistake, but you should aware that like um yeah, we can do that just because this is essentially the same thing after marginalization over y. So if I do that, right, if I write like this here, then I have this is equal to expected log uh, p. My px given y can be written as pxy over py, right? Minus log px, I can absorb together, then I will have px py. So it becomes something like that. Or I can write it as a summation here, say x and y, pxy log pxy over px and py. So you okay, you can see that like this thing here, pxy you can think of as a function over x and y, and pxpy as another function over x and y. So and maybe I can call this function like pxy like f1 or actually I don't need to call it a name for that really. Let me call it some name. Let's say like this is p. Let me call this q here. So qxy is a function is essentially equal to pxpy. Let's say, and then this thing here we can rewrite as something like called a Kel divergence between like pxy and qxy. So qxy here is just pxpy, where in general like the Kel divergence of like uh, let me draw it, write it here. KL-divergence definition here. So maybe have a different color here. I have KL-divergence between let's say Px and Qx will be equal to sum over Px log Px over Qx, something like that. So then you can see that like what Ixy is actually just the Kel divergence between Pxy and Qxy, where Qxy is the product of the marginal probability of like x and y, of the PM marginal distribution of x and y, distributions of x and y. And let me like before talk more about the Kel divergence also um, look at the conditional entropy as well. So when I have like hx, let's say if I have like h is given y and hx, oh yes, sure. Yeah, actually maybe I start here like I don't think like this is useful here. Let me erase this one. So okay, before we get into like more on Kel divergence, let's look at also the conditional entropy and the conditional mutual information. So let's say I have like x and y, and look at the difference here, x, y, and z. So do you know any of you like remember what is this? Like this is another question here. You can guess. Like basically, you may not. Also, like we mentioned that like I think like two classes ago, I guess. So I think like I mentioned that like I had because of the homework assignment. Yeah. So it is to be some mutual information, but related to X, Y, and Z somehow. So just think of like, yeah, it's slightly different from, yeah. So think of like, okay, X and Y. So you're given Y. So look at these two things like here, both of them are given Y. And given Y, and we look at like what's the information we have for X, the difference between what was the information we have for X, and then what's the information of X, given that we all also know Z here. Uh, cl- Close, but you should use an I here. Um, so H, when you say Hx Z given Y, that will be like the entropy of X and Z given Y here. So actually this thing will be equal to Hx given Y plus H C given XY, something like. Uh, so cell uh, zero and three have the similar answer. Uh, not quite white as well. Like, okay, so I guess like this one is hard to recall. Like it's like two classes ago. So it's like I X and given Y, right? Given Y, it's given Y, and then you look at like in both cases you're given Y, right? So you look at like the first one is like I don't know C, and the second one I know Z, right? It's actually the information like between X and Z given Y. And this definition is asymmetric, yeah. And this is a, so therefore it's also equal to H C given Y minus X Z given XY. So of course I need to show that this is actually symmetric, but immediately you can see that it is symmetric. So um, this one here, I avoided expectation again, is expected minus log P X given Y here. Again, I use all uppercase here, as you can see, like be careful with that. And then minus expectation minus log P X given Y and Z. And then again, it's just like what I did before. Maybe I rearrange that, like expectation log P X Y given Y and Z here. Again, like you see, like I'm going to absorb this into one expectation, but as I mentioned earlier, you may or may not able to do that. Like you should be careful with that. Like I can do that because I here when I do expectation here, it's really expected over x and y here. But when I absorb this here, this is expected over x, y, and z here. But because again, like this one does not depend on z, and I expect it over z here, this will just give back itself basically as the same argument here. I guess I may have erased that. So then therefore like this is actually these two are equal when I absorb that. Um, so and this is equal to log p. I can use base rule here. Px given y and z is equal to p. Let's see, px z given y over p x. Let's see, yeah, py given pc given y, right? Yes. Yeah, I think it's right. So therefore, like I substitute that and I absorb this minus log p. Instead of writing minus log p, I can just say maybe I just write this one more step. X xc given y over pc given y, right? Minus log p x given y. What I mean is I can have like this, just put it here instead, right? So then have a log p x z given y, pc given y, px given y. That's the conditional mutual information between x, z, and y. I mean, you can see the definition is symmetric now. So actually, this at the end, I can write this thing like start defining as this one, but eventually it's equal to this expression, right? But this expression is symmetric, like symmetric in the sense I can replace x by z and so on. I can swap x and z, and it's still the same thing here. So therefore, like this show that these two should be the same, right? These two should be the same. Again, like if you look at this one here, this one is doing a expectation over x, y, and z, right? So I can write this as p x y z. Let me write it as a sum here, x y z here, and log p x z given y over p z given y p x given y here. Now this one here I can expand that as p y and p x z given y here. So then I can rewrite as a sum over y p y sum over x and z p x z given y log p x z given y p c given y p x given y. So then if you look at this one here, this one is really sum over y p y, and this is like a Kel divergence again of like x and z. But y is like a parameter, kind of like a parameter, like parameterize like the PMF of like PXC given y and this one, this conditional, this product of this conditional probability distribution. What I mean is like this is I can write it as a Kel divergence between P PMQ, but actually this depends on y here. Maybe I write P xc given y. Okay, I'm not sure this is a very good notation, but x given y, p z given y. So but again, like what I mean for the conditional entropy, it's not by itself is equal to the KL divergence of something, but it's a weighted sum of KL divergences, and weighted sum by py for different y there, and for different y you look at the what's the difference between like when I say the difference because I'm jumping ahead a little bit. Um, the um, the intuition for the KL divergence is you can think of that as a measure between two distribution. For example, KL divergence PMQ, you can think of like um, how difference between PMQ, that two distribution. So here, like I'm computing KL divergence between like PXC given Y for a particular Y that for different Y, how's the PXC given Y is different from PX given Y and PC given Y. And if the difference is bigger, then like this KL divergence is bigger. And if like these two are identical, then the KL divergence will be equal to 0. That we will show that. Actually, you can see that right away here. Right? It's very easy to see that. If like PMQ is the same, then this will be just equal to 1, right? So then log 1 is just equal to 0. So when P is basically, if the for KL divergence PMQ, if these two are the same, this will be equal to 0. But we didn't show that like um, this has some kind of like measure property here. So for this kind of like work like some kind of magic, even though it's not strictly speaking, it's not. We should it should have some property like if like this PMQ are the same, it should be equal to 0, and if they are not the same, it should be bigger than 0, something like that, right? So I will show that basically. Okay, this is the KL divergence. Okay, let's go to trying to talk more about KL divergence. So now some property of KL divergence. Property. So actually KL divergence is Kullback-Leibler divergence. But I guess when you say KL divergence, it's okay. Like everyone kind of shorthand to say it's KL divergence. Also like also in many information theory textbook will call it relative entropy as well. And for okay, first property, like as I mentioned already, like if I have KL PMQ here, it should be equal to 0 if PX more or less if you think PX is equal to QX, then if the two distributions are the same, then the scale divergence will be equal to 0. Now we want to show that KL PX, okay, maybe just write PMQ is bigger than 0 if Px is not equal to Qx, something like it should be always bigger than. So it should be like kind of like if it's for it to be a metric, at least I want this to be bigger than 0, right? So it shouldn't have. If you measure distance or something, then the distance should not be like less than 0, should not be negative. So let's see. So I have like this one is px log px qx, right? And so let's see, I can write this as minus xpx log qx px here. So by the way, like here, I would use a lateral log. So, or like, let's see, if I want to use lateral log, I xpx, I change it to lateral log, I equal to log qx over px over log 2, right? So this gives me lateral log, right? So it's some kind of constant. I can pull it out here. Minus log 2. And something like that. And now I will use like some very simple like inequality. Know that like if look at the lateral log function here, log x, what do you have like for log x? So when x is like negative, it should be undefined. So when x is like minus infinity, it should be like minus infinity as well, right? Log 1 is should be equal to 0. So this, let's say this is 1, log 1 is here. So it have a shape more or less like this, right? Log function, something like that, right? And then like you think of like what's the derivative like for log x, let's say fx is equal to log x, f derivative is equal to 1 over x, right? And if I look at f derivative when x equal to 1 is exactly equal to 1, so therefore like here like the slope here at 1 here is exactly equal to 1, right? So I have something like that. If I draw a line here, let's say this is like y equal to x minus 1, let's say, right? This will say a line y equal to x minus 1. This have a slope is equal to 1 and also like is equal to 0, y is equal to 0 when x is equal to 1. So it's just like tangential like to this y equal to log x at x equal to 1, right? And apparently like because this log function is concave, then so I should have like y, basically this curve here, this line here, y equal to x minus 1 is always on top of like log x, right? So I should have like x minus 1 is bigger than equal to log x. So I have a very simple inequality here. And also like this equality hold if and only if like x equal to 1, right? So therefore I should have log x is a bigger than okay, less than equal to x minus 1. Therefore minus log x should be bigger than equal to 1 minus x, right? So therefore I will have this one minus log x here is bigger than equal to, I mean I ignore all this here, denominator, wait a sec, what's the denominator of the last term on the right? You mean this one here? It's qx over px. Yeah, this is qx over px. So I have log base 2 earlier and I convert to the one before that. You mean px here? Before the sigma. Oh, okay. Yeah, this is log 2 here. Yeah, sorry about that. Yeah, lateral log of 2. So here I just say usually we use the unit of like bit, so therefore we use log base 2, right? So here like I want to use lateral log instead because I have this inequality. I want to use this inequality, so I convert to lateral log. So convert to lateral log, I have like log this thing, like log 2 of this is equal to lateral log of this over log 2, something like yeah. So but this is actually really a constant. It doesn't matter like at all. So I will have like, yeah, this is more or less all constant, right? Log 2 here, I can copy that sum over x, px here, minus log something now is like bigger than equal to 1 minus x, right? Bigger than equal to 1 minus, now this is actually x, right? So qx over px here. So therefore it's equal to log 2 sum over x, px. So I have px here minus qx here, right? But if I sum over that, it's like just two sum here. I sum over xpx and sum over xqx here. What's that? So what is this? Actually, maybe I should just say, well, what is this? Maybe a question of what is this one? Yeah, summing over sum over. Yes, that's one way because I um remember like actually whenever we do this one, like the sum over px, yeah, sum over, yeah. So whenever we talk about Kel divergence, like, the argument there like is always we assume that is to be some distribution. So this should be like some distribution as well. So therefore, like they should sum over to one. So I have like this is one, and this also sum over to one. So therefore, like I will just have one minus one. So therefore, it's just equal to zero here. And note that like this is like the proof here. If you go through the entire proof, like I have this whole thing is bigger than equal to zero. So um so I have that bigger than equal to zero. Uh m is equal to zero only when here I have the inequality here, right? So only when like this inequality become equality, I can have this KL divergence equal to zero, right? And when does that happen? This happen when the condition, this one, right? When x is equal to one. Note that the x here, yeah, maybe I forget to copy that. Like, yeah, sorry about that. Let's see. Yeah, I can put minus sign, but it doesn't. Um. Oh no. No. Sorry, the minus sign is absorbed to here. Yeah, yeah. Minus sign. I'm okay. Maybe I put the minus sign here. Just yeah. Just put the minus sign here. So because I minus log, I have this earlier. Right? Minus log something is bigger than equal to one minus x. Minus log. Maybe I don't. I shouldn't use x here. Maybe I call it w here. Minus log w is bigger than equal to one minus w here. And the equality happen only when like w is equal to one. Yeah, now I call this w now. So what's w? W is like qx over px, right? So only when qx is equal to px, then this inequality can become equality. So meaning that like I will have like this one is always bigger than zero when P and Q are not the same. And P and Q are the same, then this will be equal to zero. Yeah. So then you can see that, okay, at least it has some flavor of like a metric or like some kind of measure. But note that like we call this divergence instead of like some kind of like metric because it's not really a metric. When we call something as a metric, it has to satisfy a triangular inequality and so on and so forth. And one special more more importantly, it should be symmetric, right? When you measure like from this from a point A to point B, it should be the same as like from point B to point A. But the KL divergence here is not, apparently it's not symmetric. I don't have like KLP and Q is not equal to KL, Q, and P. So this is very apparent from the definition here. So if I have like, this is like KL, P, and Q. So if I have KL, Q, and P, I will have like X, QX log QX, PX instead. So apparently they are not the same. So is that clear? So be very careful for that. Actually, KL divergence are not symmetric. And now if we back to what we talked earlier about like mutual information, conditional mutual information. I have mutual information is essentially the KL divergence between like joint PMF, PXY, and the product of marginal PMF, PXPY, right? And note that the mutual information is equal to 0 if and only if these two are the same, right? So if I have like PXY is equal to PXPY, then IXY equal to 0. So what does that mean? Like what will we say for X and Y for this situation? When IXY is equal to 0, what happened to X and Y? Yes, X and Y will be just independent, right? This is a basic definition of independent, right? That's precisely what we expected, right? So if there's no information shared between like variable X and Y, they should be just independent. So and then I should have like hx minus hx given y is equal to 0. I mean, if you look at that, it's also very reasonable. So then in the sense like, if you look at hx given y, or like then this will be essentially x and y independent, then ixy equal to 0, then hx is equal to hx given y, or hx given y is equal to hx. So knowing some information of y, I mean, if we try to like see what's the remaining information of x, it will just as like what's remaining information of just x alone, because y is not helping at all, because x and y does not depend on one another. And if you look at conditional mutual information, something similar, right? So we have the conditional mutual information ixy given ixc given y. So we say earlier ixc given y is essentially these two things, right? So if it's a little bit more involved than the mutual information case, because it's not immediately equal to a mutual information. But if you look at that, it's just saying that like, if I need these things to be equal to 0, so know that like mutual information, the KL divergence is always positive, and Py is always positive. What it means is that like if this is equal to 0, each of these has to be equal to 0, right? For all Py, so what essentially to say like if this is equal to 0, that means that like for all y such that Py is not 0. So for all the y that can happen, that Py is not 0, I need to have the KL divergence between like Px c given y is the same as a px given y, pc given y. This term has to be equal to 0. And this term equal to 0, meaning that like I should have like px c given y for all y. Okay, I already have like 4. I have like for all y, py is not 0. I should have like pxc given y equal to p is given y, pc given y. So that essentially just means that like x and c are conditionally independent given y. So, and again, it's very reasonable. Right? It's just like, okay, if the mutual information between x and c given y is equal to 0, just means that like x and c are conditionally independent given y. So, and I'm also implied this thing like x given y is c minus hx given y given z is equal to 0. So this one is equal to 0. Or like I should have hx given y and z is equal to hx given y. So again, like in general, I should have this one is less than equal to hx given y, right? But in this case here, like if given y, x and z are independent, now if I already really given y here, even though like I have z is given, the amount of information for x will not be smaller. It will be still the same as a amount of information of x given y alone. So okay, that's something about conditional mutual information and like the relationship of like mutual information. Maybe. Okay, just to be sure. Maybe just right here as a summary here. So I have like ix y equal to 0. Then I have like x is independent of y. This is like also like Kel divergence. Actually, maybe I write like this. This is like Kel divergence of like px y px py equal to 0. P essentially this is like honestly this is a if you are very picky with this is not exactly the same because um Kel divergence this one is equal to 0. We enforce that like um, pxy is equal to pxpy, but this only matter when pxy is non-zero. So for the case like when pxy is equal to 0, actually we don't care. But okay, for most purposes, we can assume this is just the same, or like be careful like. Non-zero. And this is just x and y are independent. So I have like ix. I use ixc, where I forgot. Ixc given y equal to 0. So if I like for all y such that py is not 0, I have like Kel divergence of like px c given y p is given y p c given y is equal to 0. And it's essentially it's like px c given y is equal to p x given y is c given y, and this is given conditionally independent with z given y. So and so any question for that? So I guess I think now is actually a good time to break. Maybe like we break a bit early. How about coming back like again like 15 minutes later on? Like my clock is like 4:12 now. Maybe like for 27. We'll come back for 27 with some other materials. Okay, I guess let's continue. And um, I get just a little bit warm up. We have those training rule for like entropies and conditional entropies. So we can define something similar with like mutual information as well. For example, if I consider ix1 up to xn and y, so I know that this is equal to h x1 xn minus h x1 xn given y, right? So then I can expand each of these, like the first and the second term here. hx1 up to xn here will be hx1 plus hx2 given x1 and so on and so forth up to hxn given xn minus 1. And then minus this one here is a hx1 given y, and then hx2 given y and x1, and so on and so forth, and hx and given y and xn minus 1. So then we can group the terms together like this one with this one. So I don't know how many of you are actually here, but let's see. So what very simple question here, like, so what is this minus this here? So f hx1 minus 1 given y here. So what was this? Yes. So this is just ix1 y, right? And so I can group like also the second term here. So, oh, how about the second one? So per say hx2 given x1 minus hx2 given yx1. So what is this one? Yeah, I guess you're right, but you need to be careful with the punctuation here. So so when you write like this is really have totally different meaning. It's like the mutual information of x1, x2, and y. But yeah, this one is really um, the conditional mutual information given x1, right? So both cases have x1 is conditional mutual information something given x1. So what is that something? Like maybe I give more, sorry, more hints here. So this is I something something given x1 is essentially. So okay, it's become very obvious, right? So okay, anyway, so it's like x2 and y, right? Conditional mutual information x2 and y given x1. And you can see the trend here. The third term will be like I x3 and y given x1 and x2, and so on and so forth. So therefore, like it will be something like I can write it in terms of a summation notation. So it's sum over I equal to 1 to, I don't know where, ix I given y x I minus 1. So here I assume x0 is just nothing. It's nothing. It's an empty set here. So from 1 to n, I believe. Yeah, something like that. So you can, like, I would say, like, I don't honestly, I don't always remember the equation for this, the formula for this one, but I always remember formula for this one. I thought this is very obvious, right? Because this is totally intuitive. So the um even though, like, I guess, like, for this one it's not that bad also, if you try to interpret that, like the mutual information of x1 up to xn with y will be just like the mutual information, like for each of the one, first like x1 with y, and then x2, sorry, like this, I have a notation problem here. Yeah, I mean, like I x I and c I x I y given x, yeah, should be something like that. Yeah, so it'll be like, oops, still have like some, yeah, okay. So the mutual information of x1 up to xn with I with y will be the mutual information of x1 and y, and then like x2 with y given knowing that x1, and then like x3 with y given knowing that x1 and x2, and so on and so forth. So actually it's still okay. Like, it's not too hard to remember this formula if you get the right insight. So okay, this is a warm up, I guess, and I guess, I okay. Uh, it's it's a good time to get you to kind of review this Venn diagram, I guess, as we mentioned last time. So now you really familiar with like I, so x, y, z here. So maybe just give you a couple exercises. So do you know what is, oops, what is this one here? So in this Venn diagram, basically the circle, like, for, use different color, for this circle is hx, and this circle is hy, and so on and so forth. And basically we have something like this, like eclipse uh, shape is like hx given y, and so on, so on and so forth. And now for the shaded green region, like, do you know what is that? Like, do you remember, like, what? This one here. Yes, yes, yes. Very good. Yeah, this is ICY. Yes. Um, how about this red region here? So the red one. Yes. Yeah, there's ixy given z. Yes. Um, and yeah, that's very nice. Yeah, and we have maybe just one final one. How about this blue one here? The blue region here. Oh, almost like you need to be careful with like HMI. Yes. Yes. Ah, so yeah, you guys are okay. I guess you get a hang of this, and this of course this Venn diagram is a quite handy. For example, like if you look at this here, you see there's actually have some kind of like inequality or formula for hy can be like hy given x and z plus I xy given z plus I y z. Yeah, I think you can show that. Of course, I say um yeah, it's actually this is actually quite handy. Like in particular, you have only a couple variables. Like this, I only few variables. But I guess I need to reiterate again. Like um the things like in the middle here is like undefined or like it can be positive or negative. So very careful, like because this can be positive or negative, you cannot have you cannot say like I guess I mentioned that last time, but like probably like it's too important to reiterate. I should reiterate. So I cannot say something like this area basically I x z is bigger than equal to I x z given y. So I this is wrong. I cannot claim something like that. So this is like a beginner mistake many people do. So because we look at this diagram, so we assume that all these areas are just as what is written down, like we assume that everything can be it's area, right? We assume that in our mind that this always should be the value should be positive, but it's not true for the one in the middle. Like for everywhere else, like in this Venn diagram, everywhere else can it has to be like positive or I should say non-zero. Um, but for the one in the middle, like it can be negative. So this is the things that you have to be very careful with. So and I guess that's that's a little bit more about mutual information. I guess I will go back to Kel divergence and I'll talk a couple applications for Kel divergence. So first thing, like I I want to show that like okay for continuous okay our definition is a focus on discrete random variable. So we say like a Kel divergence of like PMQ is something like a summation of PX log px qx, something like that, where it's exercise some alphabet of x. So, but this naturally can extend to like continuous random variable. So in that case, like instead of PMF here, we will have PDF, and instead of summation, we will have integral. So we'll have like px log px qx, so just dx. So just we have integral instead. So like I can talk about PMQ. So they are now continuous. And basically, we can also use the essentially the same proof. Like if you look at the proof we showed earlier, it doesn't matter this is a continuous or a discrete, whether it's a whether the variable is continuous or discrete, or like whether this function is like PMF or PDF, we still have like Kel divergence PQ will be equal to 0 if P and Q is 0, okay, P and Q are the same. So otherwise, we will have like this Kel divergence like bigger than 0. So and we can use that to show that like Gaussian distribution. So if you remember, we mentioned Gaussian distribution earlier. So Gaussian distribution, let's say we just consider a kind of like single direction, not one-dimensional Gaussian. So we have X is a Gaussian with some mean mu and variance sigma square. So if you remember, the PDF is more or less like that, 2 pi sigma square exponential minus mu minus x minus mu square over 2 sigma square. So this is px like this. And so for continuous random variable, okay, for if we recall earlier, for discrete random variable, if I have something discrete, okay, maybe I just write here, if I have something discrete here, x, and if I have the alphabet size is x here, like cap x here, I will have this entropy of x will be bounded by the log of the alphabet size, right? Log base of the alphabet size. Simply because if I have like say 8 outcomes here, then can I just put these 8 outcomes coded like into 3 bits, right? So I can use 0, 0, 0, and so on. I coded these 8 outcomes. So therefore, like to store this any random variable x with like 8 outcomes will not need more than like 3 bits, right? So therefore, and we have a formal proof for that, like using Jensen inequality like earlier. But for continuous random variable, like if I have like y is continuous, let's say y is continuous random variable. If we look at hy, can we say something like that? Like, okay, maybe it's a question like hy. Do you remember like, okay, without constraint, is hy a bounded, b or unbounded? So bounded, I mean that like there's something, let's say m or f such that hy will be like less than equal to m. So m is like less than infinity. No, y can be anything. So y can be just like some continuous random variable. Any kind of continuous, maybe for example uniform, like yeah. Um, third line here, unbounded. You mean I see? Okay. It's a continuous random variable. Yeah. Yeah. Yes, actually, without any constraint, like we probably should consider it to be unbounded because I think of like even for continuous case, sorry, not continuous, for uniform case, remember like if I have something like a random variable take a range, for example, from 0 to d, let's say, and d is a uniform, then the entropy for this one will be just log 1 over d, something like, okay, log d basically. The entropy will be just log d. Then without any constraint, I can d can be go to infinity as well. So okay, I can make it arbitrarily big. So then like this entropy itself can be arbitrarily big as well without any constraint. So unlike the yeah, of course, I guess this question is a bit vague as well because my d you can complain that like my d is allowed to go to infinity. Um, yeah, but any case, I want to say without any constraint, if I allow d to be anything, then really this will be unbounded, right? If I set an m something like say m will be something like hy is less than equal to some m here. Now I only need to set d equal to 2 to the m, then immediately I will have like hy will be bigger than like m here, so therefore it's unbounded. So so therefore like unlike discrete random variable, like for example, if I say if I want to maximize the entropy, if I don't add on any constraint here, if I don't add on any constraint here, it's not a valid question. It's not a well-defined question. No well-defined problem. So and also like if you remember, like we derived the entropy for also like for Gaussian random variable as well. Like we have hx is a I think it's something like maybe I'm wrong, 2 pi e sigma square, something like that. I think that's a 1/2 here. So again, you can set like if you pick arbitrary sigma, then your entropy can like go kind of like as large as you can as you want. And often like that's an interesting question to look at is like what's the maximum entropy? You will see like that can be like different application for that, like trying to maximize the entropy. So for one thing is like um if you think of like physics, like thermodynamics, like if you let the system to continue to evolve, it will become like the system will become more and more chaos, or like yeah, not sure chaos is a good word. Um, and the entropy will just like become bigger and bigger. The second law of thermodynamic. So if you allow the system to continue to evolve, then you expect that the entropy will be maximized somehow. It's like a process of maximizing the entropy. Um, so and you want to look at the steady state probability as actually will be equivalent looking at the distribution such that the entropy is maximized. Um, so therefore, like a good question to ask often is like, what's the distribution that maximizes the entropy? But as I mentioned earlier, like here, as you see, like if I don't put in any constraint, then um you can have like as the entropy as big as you want. But in reality, it won't because like uh if you for example, like if you allow the variance to be infinite, then if you look at the energy of that system, the energy will be infinite as well. So therefore, like at least for one thing, the variance is not supposed to be infinite. So, and a good question to ask, therefore, is like, um, what is the maximum entropy given a fixed variance? Because oftentimes the energy is actually proportional to the variance. So, and that's one important result is that I'm not sure I should put a theorem. Like theorem is uh, for any PDF px of some continuous random variable x with variance sigma square, hx is bounded by 1/2 log 2 pi e sigma square. So in other words, like, by the way, this is basically the entropy of the Gaussian distribution with like variance sigma square, right? So, or, it's Gaussian. When it's a normal distribution, like the entropy is maximized. So we can show this using Kel divergence. So I think therefore it's a good time to talk about this now. So let's say let me just shorthand the notation here. Um, let's say like I have the PDF for the normal distribution, like, and maybe I erase here so I have some space here. Use a different color, maybe green. So I have the PDF. Let me just, I'm not sure. Okay, I hope it's not too hard to read. So let's say consider the PDF of a Gaussian distribution with mean, mu, and sigma square. So I have like an x, mu, and sigma square. So I will just write it as like phi x here. So let's shorthand as phi x here. So and so essentially that just means that this is phi x. So let me write this as phi x here. Now I can think of like any distribution. Let's say let's use p again. Okay, let any distribution p here. So any distribution p. If I look at the Kel divergence of like p and phi here, it should be like bigger than equal to 0, right? Simply because okay, Kel divergence is always bigger than equal to 0. And this is equal to, it's continuous random variable, so I should do an integral instead. I have like px log px over phi x here. And this is equal to just hx minus hx, right? So, or maybe I expand that like px p log px my dx minus px log phi x dx. And this is just minus hx, right? This is minus hx. And then the next term here, okay, let's look at this. I've log phi x here. Phi x is just like this one, right? This is a constant multiplied by exponential, this whatever thing. So now I have like integral px, and then I take a log of this thing here. I have log square root 2 pi sigma square, and then I have log of this thing. I have minus x minus mu square over 2 sigma square. And dx here. So here is the key step. So know that, what do I have? Like this one is just a constant, right? This is a constant, right? This is a constant. And then the second term here is trying to compute what? It's like compute x minus mu square over 2 sigma square. And if I look at this, okay, what maybe I just like write it out like okay, maybe I just write it separately. Look at, consider this, like that's just some constant. I pull out the constant here. It doesn't matter. Minus 2 sigma square. I just focus on this term here. Px like x minus mu square dx, right? So what is this? A question here, what is this? Yes, but what's this in this case? Like, you can go further than that, right? Just for this integral, what's this precisely? Actually, know precisely what the value of this one. Oh, by the way, like I'm not sure I emphasize that. Like px is any random. Okay, px is any random variable, right? For any px, any x is any random, any continuous random variable. Px is the PDF, but x have the same mean and variance as phi x here. So therefore, like I should say x has a mean of like is equal mu, and the variance is variance. I guess it's very obvious once I write like this. And the variance is a is equal to sigma square. Um, and you looked at this one and this one here. Yes, it's just sigma square, right? So we consider this px here, right? This px here, the this px will have the mean mu and the variance sigma square, and this is essentially just compute the sigma square, right? Compute the variance, so therefore it's just compute the variance, so it should be just equal to sigma square, right? So actually, I don't even care about like what I mean expanding that, but the point is like you look at what I'm computing here. Here I'm trying to compute. This is like doing expectation of just a constant, so it's like just itself. And this is like doing an expectation of x, the deviation of x from the mean, the square difference of x from the mean. So therefore, we just give me a variance. Um, and if px have the same mean, share the same mean and variance as phi here, where phi is like the Gaussian distribution here, phi here with the same mean and variance here, then this one, this integral here is essentially the same. Even I change this p into phi, right? So I mean, like this will be the same as phi x log. Yes, yes. So we that's what I mentioned. Uh yeah, I guess I didn't articulate very well. What I mentioned like earlier is that like we need to have some constraint. So px, like okay, if like px is arbitrary, then will be unbounded basically. But if I let's say I have say consider any distribution with some mean mu and variance sigma square. So what will be the maximum possible entropy for that one? Uh, the claim of this theorem is saying that the maximum entropy will be just the one that with the same mean, or like actually mean doesn't matter really, with the same variance uh, as this px, but it's Gaussian distributed. So, and now if we let me repeat the proof here up to this stat here. So we start saying that, so we're saying that like, okay, P can be any distribution now, any, I should say like P can be any PDF now, but P has to have the mean is equal to mu and the variance equal to sigma square, let's say. And phi is actually the Gaussian PDF with the same mean mu and sigma square. Now I look at the Kel divergence between like P and phi here. Now it has to be bigger than equal to 0. Then I rewrite in the Kel divergence here. Then I expand that. Then the first term is just the entropy of x, like minus hx here. And then the second term here is equal to this. Now I expand that. If I look at that, like I'm trying to do expectation of a constant and also um, uh, how x is deviate from mu, basically the square difference of x and mu, and that's essentially just the variance, right? So therefore, like if I change this px to find x, the value doesn't change, right? Because this is essentially the same. Of course, I can continue to write it out, but then you see like it's the same as well. Like yeah. So I do you guys agree with that? Like, if not, I can expand that. Like the first term apparently will be the same, right? Because this is just a constant. So I take an integral of that. Like both case will be just a constant, just equal to log 1 over 2 pi sigma square square root. And then the second term, this one, if I take the integral, is the expectation of that. This give me sigma square over 2 sigma square minus 2 sigma is equal to 1, I mean, equal to minus 1 half, right? And if I don't have px, I have sigma x here, still I will get minus 1 half, right? Because in that case, sigma also have the variance equal to sigma square. So is that clear? So, but if I write like this, I replace px by sigma x here, then now I can go back. This one I can rewrite as a sigma x, right? Find log find x. Okay, this I can rewrite back. Just group them together again and write that back to the original here. That's log find x, right? Log find x here. And then of course this is just h find, right? Or like the entropy of the Gaussian distribution, right? I actually have a plus sign here. So therefore, I can move this to the other side. I will have like h phi here is bigger than equal to hx here. So here I write h phi. Okay, this is like another kind of like overload of notation here that people often do. Like if you have, for example, like I have hx, maybe like I have like more often like hx like is basically, you know, this is a uh, px log px dx, right? It only depends on the PDF, right? And so therefore sometimes like people all can also write hpx, like even though like we write hx like actually more intuitively think of like the amount of information of like variable x here, but it's actually only really a function of px instead, right? So therefore like sometimes people write interchangeably like or hpx or something like that. So um here in this case I write h5 like in the same basically by the same argument I write h5 here. So is that clear? So then we have basically we show this is a one very important result that I think is a something again like a take home message, like I assume that even you after you finish this course, like a few things you should remember. Like this is one thing like you should remember. It's like for any random variable, if a fixed with a fixed variance, um, the random variable will have like maximum entropy when x is like okay, I guess I when x is like is Gaussian, yeah. Okay, I have a crying baby problem. I don't know how. Hopefully the mic doesn't. Yeah. So any questions? Hey. So okay. I guess I this is like for yes. If it's not Gaussian, it's not maximized. The Gaussian have the for the same variance. A Gaussian have the maximum entropy. Yeah. Because I for the Kel divergence, remember like um this is this inequality will become equality only when like p and phi are the same. So essentially, I need to have like the PDF of that x to be the same as the Gaussian, so that it will be maximized. Yeah. And so this is like for single kind of one-dimensional Gaussian. We can also look at the multivariate Gaussian. So maybe I'm not sure I give all the steps here. So we can describe multivariate Gaussian like that. Like so I have x, I have a like a vector here, vector x with mean mu, and then I have use a Coenzyme matrix. Maybe I write sigma s here instead of sigma. Often I write sigma, but I guess like my handwriting is kind of bad, like that may confuse with the summation. So I often like in textbook we will use sigma instead, like for the variance for Coenzyme matrix. Basically, like I have like S. This is a matrix here. Let's say X, like let's say X is some vector, maybe like X1 up to X, and here then the mean, of course, is just like expectation of this big X here will be just a expectation X1 up to expectation Xn here. So I vector like that. So this is the mean. Basically, this is the mean. So and the Cohen matrix, like let's say S for the ij element will be just the expected value of xi minus mu I, the ith element of that basically like expectation xi. and xj minus mu j. So this a multivariate Gaussian distribution. And if you're given the Cohen's matrix and the mean here, so this is known as a S is a, as I mentioned, most books will use sigma. So it's the Cohen's matrix here. And maybe I can give a two-dimensional example. I don't know, like maybe I just have like two variable, maybe just x and y, maybe just x1 and x2 here, right? And my mean may be like mu just say 0, 0, like 0 mean, let's say here. And my Sij, let's say, is equal to, or like sigma, S is equal to 1, 1, 0, 0. So then in this case would be like, I have if I sample points here, let's say now I'm doing is I sample points from here, let's say here's a Gaussian distribution, like with this mean is a 0, 0, and covariance is a this identity matrix here. If I sample point here, so I will say more or less say something like that would be like calculate with the loss of point sample near 0, 0, and then more or less say some points scatter away from the origin. And I can have another example. Let's say S is equal to 2001. So let's say, okay, let's see like whether you can guess like, so let's say for this second case here, so this second case here, let's see, maybe I'll use different color here. So what do you think? Like, so let's say this is x1. This is x1, S is for x1, this is S is for x2. Should the points like this? Or like this? Or the original green one. So I don't know, like the red one is like, let's say green one is like B, let's say, and then B is a, oh sorry, B is the blue one, I'm sorry, and then red is A, let's say. Maybe I also include the green one I see here as an option. So which one should looks more like sample from this S and this mu here? Yes, that should be like more or less say you have for the x1 dimension is kind of spread out, and like because of a higher variance, and then along the x2 direction is like less spread out. So okay, how about something like if I have something like that, so yeah, so I will have something like S is equal to, let me guess, hey, what does it look like? Um, 2 1.5.5 maybe. Uh, or 1112 or 2. It's hard to make this kind of choices here. Maybe this is quite silly choices, right? So which one look more like this one? Maybe none of above, I guess. Like, I don't know. Yes, I will guess A. Uh, but yeah, okay. My point is say, okay, the off diagonal element. Let's see. Should be larger than 2. First element should be larger than 2. Uh, yeah, I don't know. I didn't put the S's here. It's hard to say. Yeah. Um, but okay, you yeah. Actually, one thing I want to point out, mostly I want to point out is like, in this case here, like this one x1 and x2 are not independent, like, but this one x1 and x2 are independent. Actually, when I have this off diagonal term is 0 here, is actually independent here. Um, uh, but in this case here, like they are actually correlated. Um, I have I have this x1 and x2 are basically like I have look at like expectation x1 x2 here. Um, this one um, if it's uncorrelated, will be equal to expectation x1 times expectation x2. Um, okay, but it's hard to see here actually. I don't know whether I should go into this direction. So um, but I graphically I can see this is a correlated because when you are, for example, if I look at like if I sample like some point like x1 and x2 here, if I sample some point here, let's say x1 a point here, right? Then I know that like x2 likely to be positive as well, right? But on the other hand, in my original example here, like if I sample a point here, like x1, so I have x2 have a range here. So for here, my given x1 is here, x2 will be have a range here, right? I'm quite sure x2 will be positive, basically. But if I sample like x1 is at here, x2 like can be anything like positive or negative. So that's very little things we can talk about x2, like x1 and x2 has to be independent. So But okay, anyway, like this is just okay. A little bit want to make sure that like you're familiar with at least like what I'm writing here, like the covariance and so on and so forth. And if the if I given you like the mean and the Coenzyme matrix here, the PDF I can write down the PDF precisely would be something like so exponential. The exponent is I think it's x minus mu sigma. Sorry, not sigma. I'm using s here. S inverse x minus mu 1/2. There's a transpose here. There's a minus sign here as well. So it's okay. I forgot like whether I have a minus sign when I write down the PDF earlier. Hopefully I do. Let's see. If I don't, then I should. Yeah. Okay. I have the minus sign here. Okay. Sometimes I just say careless and forget to put in the minus sign. So the exponent is like that. The scaling factor, like I think is okay. Most likely I need to look for that. I think it's like this. Maybe I'm wrong. Yeah, I think it's like something like that. Yeah. So and we can, and I guess I probably won't going to show that this is a have the will be maximizing the entropy as well. So in this case, it's like if you have a continuous random variable, continuous multivariate random variable with some mean. Actually, mean doesn't matter because mean a different mean basically just different shift of their variables. It won't change the amount of information there. The entropy will be the same. Uh, but if we fix the Coenzyme matrix there, the maximum covariance will be when that distribution is Gaussian-like as well. So therefore, like in multivariate case, the maximum entropy will basically when I have like the distribution kind of like behave like this one. And you can essentially do the same proof, like if you want. The similar proof here, like as before, if we go back there, if you look at this proof here, we can essentially do the same thing. Like we say, like for any px here, say anything with the fixed mean. Now instead of the mean and variance, we look at mean and the Coenzyme matrix, like maybe some s here. And then we consider phi will be the entropy of the multivariate Gaussian distribution. And then the steps will be more or less the same. And then you go down and then you look at this one. Again, like that one here, if you expand that, you'll find that like the terms here will only depends on the um, covariance and also a constant. So in that sense, like we can again replace the distribution from P we find there, and then essentially it's essentially the same proof basically. So here maybe like I won't repeat this entire step here. Instead, I was just trying to find the entropy for this one. Let's say for this distribution, like if I have a multivariate Gaussian, so what will be the entropy for this one? So this will be let me call this phi again. So phi x here, phi x. So it's phi x vector here. So I compute the entropy phi x here. H phi, maybe I write. So it's basically I expand that like minus phi x. I have log 2 pi sigma. Oh, sorry, I use S. I say like I'm going to use S here. 2 pi S. There's a 1/2 here. Determinant 2 pi S 1/2. There's a minus sign here as well. And plus, actually another minus 1/2 x minus mu transpose S minus mu. Oh, okay, wait a sec. Like I shouldn't really expand that. I okay. I guess I'm not sure. I should cross it out. I think I can just get away writing the expectation instead only without the. Yeah, I don't think I need to. Yeah, it's okay. Maybe I just write here like expectation minus log phi x here. So then I have like minus expectation log determinant 2 pi s and minus expectation. I have 1/2 put it out here. X minus mu transpose S inverse S x minus mu. Okay, yeah. So this is just constant. Okay, let's forget this. This is just log, and then I have this minus sign log 1 over something will be like have a minus sign of something. I will have just log. That minus sign will cancel with this minus sign here. So I log determinant 2 pi s here. So for this term here, I unfortunately I need to expand the summation. So I have like minus 1/2. Yeah, actually I have log here. I better put a log e here also, like because that is actually log base 2 and my exponential is a e exponential here. It's okay. Log base log e2 log e here. Let's put a log e base 2 here. And this expectation I can expand this matrix multiplication here. So if I the x minus mu the ith element. Oh, by the way, like I assume you guys have a good handle of like kind of like matrix multiplication, linear algebra, and so on. Note that this is a scalar here. This is a column vector. By convention, in engineering, in most area, whenever we, in particular in signal processing, when we write a vector, we always assume it's a column vector. So therefore, like I have x, like let's say this is a n by 1 column vector here. This Coenzyme matrix is a n by n, right? So the inverse is also n by n here. And the transpose of that column vector is 1 by n. So it's like 1 by n times n by n times n by 1 is just a scalar value here. Of course, I expect a scalar value here because this is a PDF, right? So it should be a scalar value. So now I can expand this way. I can, for example, like A, B, like if I look at the A, B element, what I mean is like, yeah, okay. Like, let me know if you don't know what I'm writing actually here. So here I just what I'm doing is I just okay let me just write at least write like this. So AB, if like AB matrix, I look at the ij element. If I multiply them together, look at the ij element of the product A times B, it will be what, like A I K B K J sum over K, right? Something like that. So and if I have like uh, A, B, C, look at the ij element, then will be like A, I, K, B, K, L, C, L, J, sum over K and L. Right? So that's essentially what I'm doing here. And now because this is scalar, I'm actually looking at the one and one element. And x minus mu one ith element is just equal to x minus mu I, because x minus mu is basically just a vector. So therefore, I in all, like basically this will be equal to this summation ij, like x minus mu ith element times s inverse the j element, and then x minus mu j element, something like that. Now let's continue to focus on this one here. I can rearrange the term where I have like x minus mu I, maybe I want to put j first, maybe let's see. Yeah, x minus mu j, x minus mu I, and then s inverse ij, and sum over I, sum over j, let's say. Now, but if I look at this one here, this is what? This is really the s, the jth I element, right? And now I look at this one here, it's really the jth element of s times s inverse, the jj element of that. And the jj element, s, of course, s times s inverse is just an identity, right? The jj element of that is just equal to 1. So therefore, this is just equal to 1, the whole thing. It's very nice. It's just equal to 1. And then this is for j sum from 1 to n here. So I basically will just equal to n, right? So I sum 1 n time. So I will just have n here. So this whole thing will just give me n, essentially. It's just n over 2 log e base 2 and log determinant 2 pi s. So eventually this is equal to I think I'm missing a square root here. There's a 1, yeah. There's a 1/2 here. I forgot this 1/2 here. There's a square root, there's a 1/2 here. 1/2 here, there's 1/2 here, 1/2 here. So then the result should be 1/2 log. This is a determinant 2 pi s times e to the n, something like. And by the way, if you look at a determinant of a matrix multiplied by the constant, it will just equal to the a to the n determinant of a. That you can show that quite easily. So therefore, I can have this e to the n absorbed into the determinant here. So then I will have a pretty nice formula that is 1/2 log determinant 2 pi e s here. So this is basically the maximum entropy you can get for multivariate random variable. When you have the coherence matrix is equal to S, the maximum you can get is that. So this is one application for Kel divergence. I guess uh, I digress a bit, like just showing that it's a maximum entropy, but then I guess uh, showing that Gaussian is maximum entropy. It uses one step. It's only use one step for the Kel divergence, but um, it looks a lot of things because like the algebra is a bit more involved. But it's all very simple. Like um, everything is on the slides anyway. If you don't follow anything, you can just look at the slide or like watch the video again. Um, okay, let's also look at another kind of application. Um, something long as the Thiel. I don't know sure I pronounce it correctly. Thiel index. Um, so the Thiel index is a something introduced by economists, like trying to measure population, like the wealth distribution in the population. So want to like measure like the how fair or like what's the economic I want to go to the slide to get the exact wording there. So want to basically it's a equality index, like so equality in the sense like equality of wealth. So think of like let's say if I have a population of a group. So let's say I have Q is let's say Q let's see let's think of that like Q is distribution of like some attribute of like a group of group of people. So for example, like we can group people according to ages and also like race and different things. Let's say maybe it's like age range, like or like we can even pick individuals. For example, like consider age. Like for example, we split like age may be more, kind of like more weird. Maybe like maybe I don't want to use race. I don't know what else I can use. So yeah, we can use race or whatever. So Q maybe like for different ways have like different distribution there. So let's say I have um for a group of like maybe like a population like 100,000 here, and then I have different races. Like maybe I just say A, B, C, D or whatever, like different attributes, right? So have a different fashion of people, right, according to different attributes. So this is a in terms of a population here. So they have like different attributes. Now I can also look at the wealth distribution um, proportional to of that group, right? So wealth in the sense like for each of the group, let's say the total wealth of this entire population is like some W here and kind of like split among all these different groups here. So maybe like group A have like more portion of wealth and group B have like less and like group C have less. Group D and maybe group E have like quite a bit more. So this is like wealth here. So have like another distribution P, right? So I can normalize all of this, right? This I can normalize this into a distribution function, and I can normalize this as a distribution function as well. Now, in the ideal case, in the sense that it's a the society is more equal, then the wealth should become proportional to the uh, how the people are grouped together as well, right? So therefore, like we can kind of like measure like the how I mean in the sense like the distribution of these two will be like similar. The more similar these two distribution, the high equality of that society, right? So essentially we can use KL divergence to measure that. KLPQ, and this is essentially the field index. So, and then and to make an example, I can even measure for not group of people, I can measure for individual. Let's say I have, instead of group them into 5 groups here. Let's say I for this 100,000 people, I just put them into 100,000 groups, right? So then in this case, my Q will be just equal to 1/100,000 here, just a uniform something. And then P will be how much money for each of the people here they own, they have. And then we, we, we can compute the, again, the KL divergence for that one. And if, okay, maybe I just give some kind of see if you guys are following. So if one person has everything, what is what will be the field index? This is an extreme case, like I'm assuming the population is n here. So that's for n is 100,000 here. Okay, you need to plug into the formula basically. So so in that, okay, okay, everyone is own group. So okay, in this case, I would just say Q, everyone is the own group, right? So Q is a distribution of what, Q will be just uniform, right? As I mentioned, will be just, I have n outcome here. Each of them will be just 1/n, just a uniform distribution here. For Q, this is for Q here. And for P indicates if there's one person own everything, right? So it will be a delta function. That's one for that particular point, and everywhere else is 0. So what is KLPQ here? Okay. This is the distribution. So okay, maybe I will step back a little bit. let me step back a little bit. So the motivation here is like they trying to measure equality of like people or like at least wealth like in a society. So then like they look at distribution of people and then distribution of wealth. And one way to compute that, like I would just assume like each people like as a different group. So then if like there's a 10,000, 100,000 people, then I would just assume there's 100,000 group. And ideally, if there's a really fair, this is extreme case, that everyone own, I mean, have exactly the same wealth, then the Kel divergence between P and Q, the Q is okay. Q is like the population, like how it's distributed. Like it would be in this case, it's like just completely uniform. Like each individual think of like as think of this way. Like Q is a you are going to sample from this population, and each person will be a group. Now I ask you like what's the distribution of like sample someone, then the probability sample a particular person will be 1/n, right? So I will therefore I will have a uniform distribution of like something like having like n outcome, and the probability for each of them will be 1/n, and and then ideal case if everyone have the same wealth, I kind of like have the wealth normalized into a distribution, then that will be a uniform distribution as well, right? So here, like in this case, like let's say like here instead of 100,000 people, I've just 5% here, like just 5% here, and okay, like instead of group A, B, C, D, E here, so now like this 5%, like I'm going to sample this 5%, so I can get kind of like randomly get one of the person with like same probability, right? And then like ideally if like everyone have the same amount of wealth, then these two like I compare Kel divergence will be equal to 0 because these two distribution will be identical. So if like someone has more money than someone else, like some actually typically what was the reality is that that's going to happen, then I will have the Kel divergence between P and Q won't be 0, will be bigger than 0 somehow, right? In the extreme case, will be like one person that just all everything, like he has everything, and then the rest will be has nothing. Then Q will be like a Kel that, oh sorry, P will be then like a delta function, right? So in that case, particular case, the field index will be the Kel divergence between, okay, again, like P and Q. P is like just a delta function. Q is a uniform function, like with just, um, so, um, okay, I guess okay, I'll just say, answer my own question here. In this case, my Kel divergence. So just need to remember the formula. This is another thing like I think like you need to know by heart basically. The definition of Kel divergence will be just like px like log px over qx here, right? Sum over x. So x is like the entire population here. Um, x can be like the first person up to like the nth person, right? And qx px is basically is equal to 1 for just one person and equal to 0 for everything else, and qx is just equal to 1/n, right? So therefore I basically have like log um, px for most values is equal to 0, but for one value I will get 1, so it's like 1/1/n times 1, and for the other things it's like just all zeros, so therefore it's just equal to log n. Yeah, okay, I guess I will just stop here. So yeah, we will come back next week. I guess I will post a homework problem this time. And by the way, okay, wait a sec. Like, are we going to have presentation next week? Saturday, I think like or later. I think I put that on in my calendar, but Yeah, I've put the presentation schedule. And Mikhail and like Dylan, like you're going to present next week. So just make sure you guys are prepared. So and I guess we will start with the I guess I will start with your presentation. So it'd be easier to control like how where I should end basically. So you can use whatever time you want. Like I want like 30 minutes, I guess. And I will also like you guys will do a peer review of your classmates, and I will put up a canvas assignment for that so that you can review for the for the others. So okay, I will talk to you guys next week then. So see you guys. Yeah, and yeah. So for any of you guys are late for assignment, please make sure try to submit as soon as possible. Even though uh, I try to cap the penalty to 50% or something like that, but um, yeah, you want to submit as um, I don't know. Okay, yeah. So okay, talk to you guys later then. Bye now.